Okay, so we got a really cool question from one of you guys.
Yeah.
And it was basically like, could you power a light bulb from a tree? Like just like screw a light bulb to a pine tree
Okay.
and like have it light up. And I thought, wow, that's
awesome image.
that's a really cool question.
It is, yeah.
And
super creative.
so we actually found a conversation about this very topic.
Oh, wow. Okay.
Where someone was talking about it, and we pulled some notes from that. And that's what we're going to be diving into today.
All right. So we're looking at harvesting energy from trees, huh?
Yeah, so we're going to try to figure out, like, how realistic is this based on what we've seen in this conversation?
Okay, cool.
Is it possible to just screw a light bulb into a tree and have it light up?
All right, let's get into it.
What's the science behind that?
So the first thing that that they talk about in this conversation is this idea of like tree voltaics, right? So the idea that there's an electrical potential difference between the top of a tree and the soil around it or its roots.
So like its own like little tiny battery?
Yeah, like a very, very small battery.
Yeah.
And so like the setup that they were imagining was like you stick probes into the upper part of a tree and into the soil.
Okay.
And then you hook those up to a voltmeter. And they were saying that you'd get like somewhere between 0.2 and 0.8 volts usually.
Right. And that's not enough to really power much of anything. I mean, my phone charger is like way higher voltage than that.
Yeah, much higher.
But I remember reading somewhere that there are some applications for that.
Oh, yeah, definitely. Even that low level of voltage can be useful for things like very low power sensors.
Oh.
Like, you know, environmental sensors that are monitoring soil conditions or something.
Cool.
Or even just like demonstrating electrical concepts in a classroom setting.
Okay.
That kind of thing.
All right. So that's like the basic concept. But then they took it a step further. And they started talking about this idea of like, what if you put the neutral or ground into the tree itself?
Oh, interesting.
Like not just the ground like into the soil, but like actually into the wood of the tree. Okay,
so you're using the roots for grounding, but then also returning neutral or ground directly into the tree.
Yeah.
Interesting.
And I was thinking like, how does that change things?
Yeah, well, basically what you're doing is you're creating a more localized circuit right within the tree itself.
Okay.
Rather than just measuring the difference between the tree and like the wider earth.
Okay.
Right. So by putting that grounding or neutral connection directly into the tree structure, you're setting up a reference point for electrical potential there within the wood.
And the roots are still doing their job of connecting to the ground.
Right, exactly.
Okay.
So now you're looking at like the very small voltage differences that might exist between different parts of the tree structure, with the soil still providing like that overall ground connection for the system. But the thing is that the voltage changes you'd likely pick up like within the tree without that bigger difference between the tree and the ground would be even smaller.
Wow.
Like we're talking maybe millivolts or even microvolts in some cases.
Millivolts. Wow, that's tiny.
Yeah, really, really tiny.
So if it was already a low voltage, it's like even harder to get power out of it.
Right. Essentially, you'd need some pretty serious amplification technology to actually draw any meaningful current from those minuscule voltage differences.
So that's probably not going to work then.
Yeah, you might be able to detect it with sensitive equipment.
Okay.
But actually using it to like, you know, power anything is a whole other story.
Okay, so back to the original question, a light bulb idea.
Yeah, the ambition to power a light bulb from a tree.
Yeah.
Yeah.
Just screwing something into a pine tree.
I mean, it's a cool idea.
Yeah.
Like visually just imagining that is really cool.
Yeah, but what does the science say about that?
Yeah. Well, I mean, based on like what we've talked about so far, with the natural electrical potential of trees, it's definitely a significant challenge. I mean, the voltage and crucially the current that a tree naturally produces is just way too low to directly power something like a light bulb.
Right.
Even LEDs, which are very efficient, still need a certain amount of power to light up.
And when we talk about power, it's not just about voltage, right?
Right.
About the flow of electricity.
Yeah, you need both enough pressure and enough flow to actually power something.
So like voltage is the pressure. And,
voltage is like the electrical pressure and
current is the flow.
Current is the flow,
yeah. Yeah.
So right now with the tree, the flow of electricity is just super small.
Okay.
Even if there's a tiny bit of pressure there.
So you mentioned LEDs. Just for context, how much power do those need?
Yeah, so a typical like low power LED bulb might need anywhere from like 0.5 watt to 5 watts
Okay.
to operate. And to generate that from like the millivolt range that we might see,
Yeah.
within a tree, you'd need some really substantial system for
Yeah.
boosting that voltage and storing the energy.
So direct power, probably not going to happen.
Probably not right now.
But then the conversation takes another turn.
Yeah.
And they start talking about like, okay, well, what about the size of a tree?
Okay.
And the fact that it interacts with the atmosphere.
Yeah.
Could that be a way to harvest energy?
Right.
And this sounded to me like it had a little bit more potential.
Yeah, so this is shifting our focus away from like the internal bioelectricity of the tree
Okay.
and thinking about the tree as like a conductor within the Earth's natural electrical field,
Okay.
right? So like tall trees in particular can accumulate a static electrical charge just because of their height and their interaction with like charged particles in the air.
Interesting.
It's kind of like a very subtle form of like the static electricity you get from rubbing a balloon on your hair or something.
Like a lightning rod almost.
Yeah, like a very, very gentle lightning rod.
Okay.
And so the idea is that you could use conductive materials, like copper wires or special electrodes, to essentially tap into that ambient atmospheric energy.
Using the tree.
Yeah, using the tree's leaves and branches as like an antenna.
Okay.
And then the thinking was that if you combine that
Yeah.
with the tree's natural connection to the ground,
Yeah.
you might be able to create a more significant voltage difference that we could actually use.
That's interesting.
Yeah.
And then, thinking about that, you came up with this whole concept for a product.
Oh, yeah, right.
You called it the tree power light.
The tree power light, yeah.
Which I thought was a really cool idea.
Thanks. Yeah, it was kind of just like imagining like what a
Yeah.
user-friendly way to like harvest this energy
Yeah.
would be
In a sustainable way.
in a sustainable way.
Yeah. So what would this thing look like?
So I was thinking it would probably involve like some kind of conductive probe, maybe something like a specially designed screw that you could just put into the tree,
Okay.
ideally a pine tree.
Right.
And this probe would then connect to like a small
Okay.
sealed weatherproof box
Gotcha.
that contains the electronics.
And this would be mounted on the tree or?
Yeah, you could probably mount it on the tree somehow.
Okay.
Yeah, and inside that box, you would have like the core of the system. So you'd have like a circuit
Okay.
designed to capture the tree's electrical potential, and then you'd need a voltage amplifier
Gotcha.
to boost that tiny voltage up to a more usable level.
And then some kind of energy storage too, right?
Yeah, and you'd need some energy storage, so probably a capacitor or a small rechargeable battery,
Okay, cool.
to provide like a steady flow of power.
And what about the ground? How would that work?
Yeah, so from that electronics box, you'd also have a wire running to a grounding rod,
Okay.
just a simple metal stake that you push into the soil near the base of the tree,
Okay.
and that would complete the circuit and allow the tiny current to flow.
And then you would connect the light bulb to the...
Yeah, and then you'd have a connection on that box to power like a low energy LED bulb.
So basically all you have to do is screw this probe into the tree.
Yeah, that was the idea.
Stick a rod in the ground.
Super simple.
And then you're good to go.
Yeah, just a few minutes to install with a basic tool.
Wow, that's cool.
And the idea is that this ease of use, combined with like the appeal of natural energy and sustainability could be a big plus.
And since it's low voltage, it should be pretty safe.
Yeah, it should be pretty safe for both like the person installing it and the tree itself.
Cool. So one question I had was about the placement of the probe.
Oh, yeah, right. Like how high up on the tree?
Yeah, how high up do you need to go?
Yeah, well, as we discussed, like generally speaking, the higher you go on the tree, the more exposed you are to the electrostatic potential in the atmosphere.
Okay.
So to get the most energy, you'd want to place it like as high up, right?
As you can safely and practically reach.
Okay, what kind of heights are we talking about here?
So for like smaller pine trees, maybe in the 10 to 15 foot range, putting it somewhere around like 5 to 7 feet above the ground would probably be a good starting point.
Right.
For taller trees, maybe 20 feet or more.
Okay.
You might want to go a bit higher.
Yeah.
Perhaps like 10 to 15 feet up.
Okay.
To really tap into that atmospheric charge. Yeah. And it's also worth keeping in mind that things like wind and humidity can affect the electrical potential.
Oh, okay.
So the ideal height might vary a little bit, depending on where you are in the conditions.
Okay, cool. Yeah.
So this is all great in theory, but you were really interested in actually trying to measure this energy yourself.
Oh, yeah. I wanted to see if I could actually detect it.
Yeah, so you came up with this simple DIY experiment.
Yeah, just a really basic way to see if you could pick up any electrical potential from a tree.
Yeah, so what did you need for this?
Okay, so for this you'd need some copper wire,
Okay.
a regular metal screw
Okay.
to act as your probe,
Gotcha.
some insulated wire to make your connections a multimeter to measure the voltage,
Okay.
and then optionally a small resistor or an LED
Okay.
if you wanted to see if you could get any tiny visual indication of power.
Oh, cool.
Yeah. And then you'd also need a grounding stake.
Oh.
You can often find those at garden supply stores.
Right.
And then, of course, you need a pine tree.
Right.
Yeah.
Okay, so how do you actually put all this together?
Okay, so first you create your positive probe by screwing the metal screw into the pine tree,
Okay.
maybe around 7 feet up from the ground.
Right.
Then you push your grounding stake into the soil at the base of the tree.
Okay.
Next, you use your insulated wire to connect the screw in the tree to one of the terminals on your multimeter.
Okay.
And another piece of insulated wire to connect the grounding stake
Gotcha.
to the other terminal on the multimeter.
Okay.
And finally, you set your multimeter to measure DC voltage.
Right.
And you watch to see what reading you get.
Okay, and what about the LED?
Yeah, if you had the LED and a resistor, you could try connecting them in the circuit
Gotcha.
between the tree probe and the ground stake to see if that tiny voltage could push any current through.
So basically you're just trying to see if you can get it to light up.
Yeah, just as like a visual indicator that something's happening.
Okay, cool.
Yeah.
And the expectation here was that you would see a very small voltage, right?
Yeah, probably somewhere in the millivolt to low volt range.
Okay. So let's get to your results.
Yeah.
You actually did this experiment, and you got some really interesting readings.
Yeah, it was really cool to see.
Yeah. So first of all, when you had your positive wire at 7 feet up on the tree,
okay,
and you connected it to the ground stake, you measured around 0.65 volts.
Yeah.
So that's confirming that there is some voltage there.
That was a key confirmation.
Yeah. Okay. And then what about when you connected the ground to a dead stump?
Oh, yeah, that was interesting.
You got a similar reading there, too.
Yeah, around 0.65 volts again.
So that means that even dead wood can...
Yeah, it suggests that even dead organic material can still hold a slight electrical potential relative to the ground. Probably due to remaining moisture and some like ongoing electrochemical interactions with the soil.
So it's not just a simple, zero potential.
No, it's more complex than that.
Okay. And then you tried connecting the ground to a metal axe.
Oh, yeah.
That was in the stump, and that gave you the highest reading.
Yeah, that was the highest, around 0.9 volts.
What do you think was going on there?
I think it was probably a couple things working together. So the metal axe would be a much better conductor than the wood of the stump.
Right.
And then also the contact between two different materials, the metal of the axe and the moist wood of the stump.
Yeah.
Could have created like a small thermoelectric or galvanic effect.
Oh.
Almost like a very simple natural battery.
So using different materials can actually increase the voltage?
It seems like it.
Okay, cool. Yeah. And then you also measured the voltage between the base of the tree and an area a few feet out from the base.
Right.
And that gave you about 0.7 volts.
Yeah.
So.
Which further reinforces the idea that there's like an electrical gradient present, not only between the top of the tree and the ground far away, but also in the immediate vicinity of the tree.
Interesting.
Yeah.
Okay. And then you connected one tree to another tree.
Yep.
And got around 0.7 volts again.
Yeah. Pretty consistent.
So different trees can have different potentials.
Yeah. It seems like they can even if they're the same type.
Interesting.
Close to each other.
Okay. But then this next one I thought was really telling.
Okay.
When you connected the ground stake of one tree to the ground stake of another nearby tree.
Yeah.
You get a negative 0.3 volts.
Yeah, negative 0.3.
What's that all about?
So that negative voltage is really important because it shows us that even different points in the ground, which we often think of as like a uniform zero voltage, can actually have slightly different electrical potentials.
Wow.
Yeah. So this could be due to variations in soil composition, how much moisture is in the ground at those specific spots.
Okay.
Or even the activity of microorganisms in the soil.
Interesting.
So yeah, it really highlights that the ground isn't like...
It's not just one big ground.
No, and not a perfectly uniform electrical entity.
Okay, and then when you connected ground to ground at the same level, you got 0?
Yeah, 0 or a very low reading.
But then you said when you changed the setting on your multimeter?
Yeah, when I adjusted it to a more sensitive setting.
You actually got zero point 0.8 volts.
Yeah, 0.8 volts between 2 points on the ground.
Wow. So it's like...
So it just shows how sensitive these measurements can be and how subtle these natural electrical potentials are.
So even the ground itself has variations.
It does, yeah.
Wow. Okay. And then finally you tested a rock to the ground.
Yeah.
And air to ground, and those were both 0.
Yeah, both 0.
But then your body to the ground was 0.5 volts.
Yeah, about 0.5.
So what does all this tell us?
Well, I think the biggest takeaway is that voltage potential arises from differences.
Okay.
So differences in the materials you're using.
Yeah.
Differences in how well those materials conduct electricity.
Okay.
And differences in the environmental conditions.
Right.
At the points you're measuring.
So it's all relative.
It's all relative, yeah.
Interesting. Okay, so we've got these small differences in potential.
Yeah.
But what about, like, large scale?
Yeah.
Like, can we power a city with trees?
Yeah, that was something you were skeptical about.
Yeah, I'm very skeptical about that.
Yeah.
So why is that?
Well, while these small-scale experiments are incredibly interesting and show that there is some electrical potential there, trying to scale that up to power, like, homes, businesses, or cities runs into some pretty fundamental limitations.
Okay.
So the biggest one is just the incredibly low energy density we're talking about.
Yeah.
So even if you had vast forests of trees,
Yeah.
the total amount of usable energy you could realistically harvest
Yeah.
would likely fall far short of meeting significant power demands.
Okay, and what about, like, the infrastructure?
Oh, yeah. The infrastructure would be absolutely massive and incredibly complex.
Right.
You'd need individual energy harvesting systems on countless trees, along with extensive networks to collect that energy and distribute it.
Right.
And then you have to deal with the fact that the amount of energy you could harvest would fluctuate dramatically with changes in weather conditions, soil moisture, the seasons.
It wouldn't be reliable?
No, it would be very unreliable for a consistent power supply. And then, of course, you'd also need to consider, like, the potential environmental impacts of trying to extract energy on such a large scale from our forests.
Yeah. So when we're talking about, like, reliable, large-scale power, we're still much better off with, like, solar wind.
Yeah, exactly. Right. Yeah. Those technologies offer far greater energy density, and they're much more readily scalable to meet the energy needs of large population.
All right, so maybe powering a city is out of the question?
Probably.
But what about just powering one light bulb?
Yeah, that original goal.
Yeah.
Yeah.
You mentioned that the voltage readings you got weren't quite high enough.
Yeah, that's right.
Yeah.
While I was able to measure a voltage, the actual current, the flow of electricity was just way too low to directly power even a small LED bulb. Which typically needs at least somewhere in the range of like 1.5 to 3 volts to light up properly, along with a certain amount of current.
But you had some ideas about how to optimize it?
Yeah.
Using those galvanic effects.
Yeah, so since I got that higher voltage when I used the metal axe on the stump, that suggests that exploring different pairs of metals, like using zinc and copper, for example, for your probes, could potentially increase the voltage you can generate.
Interesting.
You could also try increasing the surface area of the metal that's in contact with the tree and the soil.
Gotcha.
To try and collect more charge.
Okay.
Ensuring good moisture and contact between your probes and the environment is also crucial.
Okay.
And you could even experiment with connecting multiple of these like tree ground cells in series.
Oh, interesting.
Just like you connect batteries in a row to add their voltages together.
Okay, so you're basically making like a chain.
Yeah, like a chain of little batteries.
Interesting. And then what about a capacitor?
Oh, yeah. You could also look into adding a capacitor to store up the tiny amounts of energy you're harvesting.
Okay.
And maybe a boost converter.
What's that?
Which is an electronic circuit that can take a low voltage and increase it to a higher voltage.
Yeah.
Although that starts to move beyond like a truly simple screw-in solution.
Yeah, so that's getting a little bit more complex.
Yeah, a bit more complex.
But then you had another cool idea, which was the forest power light.
Right.
That could light an LED without a capacitor.
Yeah, without even needing a capacitor.
Yeah, and how would that work?
So the idea here is to create a small chain of these like natural, very low power batteries.
Okay.
So you take multiple pairs of different metals.
Okay.
So for example, like a zinc coated nail
and
a piece of copper wire.
Okay.
Or a small copper plate.
Right.
And then you'd place each of these pairs in contact with a different tree.
Okay.
Or in different patches of moist soil nearby.
Gotcha.
And then you connect these metal pairs in series using regular wire.
So you're making a chain.
Yeah, you're making a chain just like you'd link batteries together.
Yeah.
To increase the overall voltage.
Right.
And then finally, you connect a low-power LED
Okay.
to the ends of the series of metal pairs, making sure you get the polarity correct.
Right. So you got to have the positive and negative.
Positive and negative, yeah.
Because so by chaining them together,
by linking them up in a chain,
you're adding the voltages.
You're adding their tiny voltages together.
Until you get enough to light the LED.
Exactly. And hopefully you reach a level that's high enough to make that LED glow.
Wow, that's really cool.
Yeah.
And how many would you need to chain together?
So if each zinc-copper pair can generate somewhere in the range of like 0.5 to 0.9 volts,
Okay.
which can vary depending on the conditions,
Yeah.
then connecting like 3 to 6 of these pairs in series could potentially give you a total voltage of somewhere between 1.5 and over 3 volts.
Gotcha.
Which should be enough to at least dimly light a small, efficient LED.
Wow.
Yeah, and some key things for making this work would be ensuring good contact with moist softwood in the trees.
Okay.
And well-soaked soil.
Okay.
And then also using clean metal surfaces to ensure good electrical conductivity.
So you don't want them all corroded.
Right, exactly.
Okay, cool.
Yeah.
So it's amazing to think you can create a light.
Yeah.
Just from the natural environment.
It's really cool.
Yeah. But then you took it a step further and you started talking about the human body.
Oh, yeah.
And how it's similar to a tree.
Yeah, it's a fascinating analogy when you think about it.
Yeah, how so?
Well, just like trees, our own bodies are fundamentally bioelectric systems.
Really?
Yeah, we generate electrical voltage through the movement of ions, charged particles, across the membranes of our cells.
Oh, wow.
Yeah, and this creates tiny electrochemical gradients, which are essentially like our cells having their own miniature batteries.
Wow, so our cells are like little batteries.
Yeah, in a way.
That's crazy.
It's pretty wild.
Okay, so what are some of the ways that our bodies and trees are similar?
Well, for one thing, both trees and our bodies conduct electricity much better when they're properly hydrated. So just like moist soil enhances the conductivity around a tree's roots.
Yeah.
Having enough water in our bodies helps with the flow of ions.
So drinking water is important.
Very important, yeah.
Okay, what else?
There's also the concept of grounding or earthing.
Oh, yeah.
You know, making direct skin contact with the earth.
Right.
Which seems to have measurable bioelectrical effects in humans.
Okay.
Potentially similar to how a tree's roots connect it to the ground.
Okay.
And just as electrochemical gradients in trees drive their growth and nutrient transport,
yeah,
our bodies rely on similar gradients for vital functions like the production of ATP, which is our main source of cellular energy.
All right, and minerals.
Yeah, and even the intake of minerals plays a crucial role in both systems.
Okay.
Influencing electrical conductivity and overall electrochemical balance.
Interesting. So you even suggested a way that our listeners could measure their own biovoltage.
Oh, yeah, right. It's a very basic experiment.
Yeah.
But you could try using a multimeter to measure the voltage potential between different points on your body and your connection to the earth.
So how would you do that?
So, for example, you could measure the voltage between your hand and the earth when you're standing barefoot on the ground.
Right.
Or you could even try measuring the very subtle potential difference between your tongue and a metal object.
Okay.
Or between the palms of your two hands.
Interesting.
Some people have even reported noticing a slight change in these readings after they've consumed, like, foods or drinks.
Oh, wow.
That are rich in minerals.
Interesting.
Which can highlight the role of electrolytes in our body's electrical activity.
That's cool. All right, so this all kind of points to this bigger picture that you've been thinking about.
Yeah.
This idea of biogenic voltage optimization for human well-being.
Exactly.
And then even scaling up the tree energy concept to create these tree grid systems.
Tree grid systems, yeah.
For remote power.
Right.
So tell us about this bigger vision.
Yeah, so the concept of biogenic voltage optimization suggests that by consciously supporting our body's natural bioelectrical functions through things like regular grounding, ensuring proper hydration with mineral-rich water, getting sufficient exposure to natural energy sources like sunlight, we might be able to enhance our overall energy levels and potentially even promote longevity by optimizing how our cells function at an electrical level.
That's pretty cool.
Yeah.
And what about this tree energy protocol.
Yeah, so that's essentially a set of daily practices inspired by these principles.
Okay.
So it might include starting your day with some time spent barefoot on the earth.
Okay.
Consciously drinking water that contains trace minerals.
Okay.
Getting some natural sunlight exposure.
Etc.
And incorporating breathwork techniques that can influence our body's pH balance and oxygen levels, all of which can have an impact on our bioelectrical state.
So you're trying to optimize your body's electrical system?
Yeah, essentially.
Interesting. Okay, and then what about these tree grid systems?
Yeah, so the vision there is to explore the possibility of creating localized sustainable power solutions for remote or off-grid areas.
Gotcha.
By establishing small networks of trees that are equipped with simple, minimally invasive energy harvesting electrodes.
So like a whole network of trees.
Yeah. And these kinds of networks could potentially power very low energy applications like LED lighting for pathways, basic environmental sensors for monitoring forest health.
Interesting.
And perhaps even simple communication devices in areas that lack traditional infrastructure.
So it's like a very localized...
Yeah, very localized, sustainable power grid.
Power grid, yeah.
Wow, that's a really fascinating vision.
Yeah, it's pretty cool to think about.
Yeah, connecting our own biological energy to the energy in the environment.
Yeah, ultimately it points towards a broader understanding of how energy flows and interacts at all levels.
Right.
From the microscopic voltage within our cells.